Okay. Let me start. Thank you, Ivan, for the introduction. So this is I'm Xingda, and this is work done with my student Fangming, Tianxia, Yuhai, and my colleagues Jingyu, Longchen, and Haibochen. So serverless computing is a new cloud computing paradigm widely adopted by major cloud providers. It aims at simplifying application development by relieving them from thinking how many servers they need to deploy for the applications. A common way to abstract the service cloud is by functions, also known as function as a service. Specifically, the user only needs to write their applications as a function and upload these functions to the platform through a container. The platform will assign a unique URL for the uploaded function and then return it to the user. After getting the URL, the user can issue a request to this URL, which the platform will start the container corresponding to the function, run the function within such container. And after the function finishes, the platform will kill the container for better resource utilization. The overall benefits of service computing can be summarized as ease of development, high resource utilizations, and economical efficiency. But the question is, what are the costs of achieving such benefits? A widely known cost is cold start, namely starting the container from scratch. Starting a container has non-trivial costs, including pooling the container image, initializing the container environment by calling all its primitives, including C groups and namespaces, initializing the language runtime that is necessary for running functions written in managed languages, for example, Java and Python, which turns to be popular for service functions. These overheads can be orders of magnitude higher than functions execution time, considering that most of the service function execution is short. For example, a report from Lambda at Edge has reported that 67% of the functions run within 20 milliseconds. To cope with cold start, the most widely used technique is caching, also known as warm start. Compared with cold start, caching will not kill containers after functions finishes. It will post it in the memory of the execution machine so that future function invocation can reuse the cache. After caching, the future function request can find the machine with the cached instance and start the container by imposing a cached container accordingly. Because the post container has already had the images and initialized the language runtime in its memory, using caching to run the function can skip many phases of the cold start, so it is extremely fast. For example, caching can typically finish container startup within 2 milliseconds compared to hundreds of milliseconds in the cold start. However, a significant drawback of caching is that it needs promotion concurrency. Because a post container can only be unposted once, so the number of cached instances deployed must be the same as the concurrent function invocations for the best performance. Unfortunately, it is challenging to estimate the number of function instances required for caching. For example, a real-world serverless trace reveals that the load spikes can cause many unexpected function invocations. Blindly caching many containers will waste many computing resources of the cloud provider. Since the platform cannot accurately estimate the number of concurrent invocations required by each function, it now requires user to specify the number of cached instances required for better performance. It is, in my opinion, fallback to traditional serverless computing to some extent. And there's no free lunch for such instances. The platform asks users to pay for them because caching will consume memory resources at the machines managed by the cloud. So the goal of this work is to achieve no promotion concurrency. The user only needs to specify whether they need to prevent cold start, not how many cache instances needed to prevent it. One optimization of caching is to execute containers through the fork system call provided by the operating system. Specifically, unlike using unpost to run the function, the platform can use fork to create a new container from a cached container for each function request. Since fork can create multiple containers concurrently, it only requires one cache instances on a single machine to warm start multiple functions. Therefore, the forked containers can be quickly killed, achieving high resource utilization. Also, we can say that fork achieves no promotion concurrency on a single machine. A limitation of fork is that it does not generalize to a distributed city. If there are many functions, we must scale them across machines, which essentially needs to deploy one cached instances on each of the machines needed for the function execution. Since it is challenging to estimate the function invocation times, it is also challenging to estimate the number of machines required by the workloads. Therefore, fork still requires OM resources, where M is the number of machines required for the applications when considering scale-out functions across machines. So now the observation of this work is simple. Since fork works well on a single machine, so can we generalize it to a remote setting? Given the remote fork abstraction, we only need one cache instance to start multiple functions on multiple machines, realizing no promotion concurrency, namely O1 resources required across machines. So the remaining question is, how can we implement remote fork efficiently for serverless computing? The remote fork is not a so new topic, which has been extensively studied in the literature. The standard approach is through checkpoint and restore. In simple words, the parent machine first checkpoints the containers into a file, which records the page table and the memory pages CPU register status of the parent container. Then we transfer the file to the client machine with remote file copy. Finally, the client machine can create a new container by mapping its virtual memory spaces to the parent's memory stored in the file, restore the page table and the CPU register status that it can run. We try this approach, but we find that checkpoint and restore cannot outperform cold start when child touches more than 256 megabytes of parent's memory. And we find it is due to the following two reasons. First, checkpoint memory to the file is costly, whose overhead is proportional to the parent's memory size. Second, transfer the entire file to the remote machine is also costly, and is typically not necessary for serverless functions because they only touches a subset of the parent's memory. So to address the file transfer issue, we can checkpoint and restore the file from a distributed file system. As we can see, when using a distributed file system, it can reduce the file transfer overhead in the restore phase because we can access it through file system call provided by the DFS. However, this optimization still has two problems. First, we still cannot avoid the checkpoint overhead because we still have to checkpoint the file to the DFS. Second, using DFS as additional overhead for functions execution. On each child's page fault, it will access the memory stored in the DFS file in a copy-on-write way. Accessing memory stored in the DFS is much slower than accessing the local file copied through the network. So the foundational problem we find for variants of checkpoint and restore is that the OS lacks the capabilities to access the parent's memory and the page table stored on another machine. Therefore, existing solutions can only store this information in the file and exchange the file across machines for remote machines usage. The solution of this work is now straightforward. Can we provide a memory abstraction such that the kernel can directly access the memory of a remote kernel by processing the file system? So the solution is viable. For example, suppose we have set up the page table for the child. Up on page 4, if the child's OS can directly send an RPC to the parent's kernel to read the page, we can skip the file system overhead for the remote fork. Therefore, we extend the OS to support remote memory accesses and add as necessary RPCs for setting up the page table and extra CPU register status accordingly. Now the OS can implement remote fork by imitating local fork with remote memory accesses. So the result remote fork can skip the checkpoint phase and execution overhead of accessing the file system. And we can see that brings a significant latency reduction compared to checkpoint and restore. Yet we find it is still not optimal because using RPC to access the remote OS memory is inefficient because it needs remote kernel stress involvement for memory fetches, and also it requires extensive memory call-based overhead. So our final observation is that the remote memory abstraction perfectly matches the features provided by modern data center networks, namely RDMA. RDMA is a high bandwidth and low latency networking feature, which provides a primitive called one-sided primitive. With one-sided primitive, the kernel can directly read the physical memory of the remote machine given its physical address using the NIC's hardware, which is much faster than RPC because it bypasses the kernel, CPU, and zero copy. So we can see that with RDMA, remote fork can now enjoy significant performance improvements and is much better than cold start. So in summary, this figure presents our roadmap in accelerating remote fork, which shows that an OS and RDMA co-design can significantly improve the performance of remote fork compared to traditional designs based on checkpoint and restore. So our final system is called MITOSIS, which is a remote fork primitive for Linux kernel. It can remote fork 10,000 containers within 1 second and is fully compatible with mainstream container runtime, for example, runc. We use it to accelerate cold start in service workload, which can reduce 90% tail latency and the load spikes with orders of magnitude memory, smaller memory usage. So due to time limits, I will only briefly present the result on MITOSIS and the load spikes. Here is how MITOSIS compared with caching and the function load spikes traced from real-world traces. With caching, you can see that it cannot achieve high resource utilization. Our evaluating platform, FN, will by default cache a function for 30 seconds. Therefore, after load spike arrives, the machine will resize many cached containers for this time period. In comparison, MITOSIS only needs one instance across the cluster, which requires much smaller memory footprint than caching. For performance, MITOSIS has a slightly higher median latency than caching because remote fork has the overhead of copy on write through RDMA, and caching still has a 60% cache hit ratio in this experiment. However, MITOSIS can significantly reduce the tail latency, since for caching, a cache miss will cause a costly cold start to execute the function. So before conclusion, I would like to shortly mention one more powerful feature of remote fork for service computing we found during our investigation. So we know that service functions are isolated with containers. So the drawbacks of isolating functions with containers is that they can only transfer state through message parsing or cloud storage. And these methods have data serialization, deserialization, memory copy, and cloud storage software stack overhead. So existing work show that these overheads can count to up to 95% of the total function execution time. So how can fork accelerate such scenario? Now suppose that we have two functions A and B, and such that A wants to transfer a piece of data to B. So if we directly use fork, or if we directly execute B by forking from A, B can inherit the pre-materialized data in A without serialization and deserialization steps. And we further using MITOSIS for the remote fork. The state transfer is also zero copy because we use the zero copy RDMA. So this feature fits the service workflow with the fan-out execution pattern list in the left of the slide well. For example, it shows a real-world service workflow FINR's execution graph. So after loading the data with a function called load data, it will spawn multiple concurrent functions run rule to parse this data. And these rules essentially need to run on multiple machines for scale out. So the data transferred is a 6 megabytes pandas data structure, which requires 600 milliseconds for serialization and deserialization. Therefore, MITOSIS can significantly outperform FN, which uses Redis for the state transfer, and also much faster than the other remote fork variants with checkpoint and restore. So there are more details of MITOSIS in our preprint. Please check this if you have interest. So in conclusion, we present MITOSIS, a fast remote fork primitive for co-designing OS with RDMA. It can achieve no proportional concurrency for service functions and also support faster state transfer between functions. Thank you for your listening.
Any more magics or details in how you actually use RDMA to do remote fork? Or it's just like simply like calling the RDMA? Do you need to change OS, or do you need to change some part of the RDMA stack?
So actually, we for the novel parts, it is just simply an RDMA request. So we changed the OS to use RDMA to fetch the remote memory. So the magic here is I think it's two things, and you can find more details in our paper. The first is how do you create RDMA connections very fastly across faster scale out containers, and we use a new technology called dynamic connection transport, and we bring it to the kernel to support microsecond scale connection establishment. And the second is how we do the memory protections of RDMA, which in the kernel we have much less support for the memory protection, which aka memory registration, memory registration MR, that is widely used in the user space. So so this I'm not covered in this talk, but you can find more details in our paper.